Welcome everybody to the first session of the last day. So our first speaker is Noriyoshi Sukegawa, and he is going to talk about diameter of polyhedra related topic. Thank you very much, Noriyoshi, to give this talk at late at your time zone. So thank you. We look forward to your talk.
Thank you for your kind introduction. Good afternoon, everyone. I am Nori. First of all, I would like to thank the organizers for inviting me to speak at this exciting workshop. Now, let me start. Here is a plan of my talk. I would like to start with a general introduction to topics of my talk, that is the diameter of polyhedra. And after that, I will get into technical parts where I would like to show some tools and approaches for analyzing the diameter of polyhedra. Two settings. And if you have any questions, please send me a message via chat or unmute to mention your question. Okay, I would like to start with a quick review on the simplex method. As you may know, the simplex method is a method of solving the linear programming problems, LP for short. And here is an image. This is a feasible polyhedron, which I denote by P. And this is a given linear objective function, meaning that this is an optimal solution, the optimal vertex in this case. And the simplex method starts with some initial vertex, say here. Then it moves vertex to vertex of P by traversing edges of P like this until it reaches an optimal vertex. And the actual behavior of the simplex method is controlled by the so-called pivot rule. And as already mentioned in previous talks in this workshop, a major open question about the simplex method is its worst case complexity. And putting it more formally, it is an open question whether there is a pivot rule that can make the simplex method run in polynomial time for all instances of LP. And indeed, bad example are, Indeed, bad examples are known to exist for almost all promising pivot rules. A well-known example would be the Clemente cube for Danzig's pivot rule. So this is an image in dimension 3 of the Clemente cube. On this deformed cube, the simplex method with Danzig pivot rule visits all the vertices like this, although one can reach the optimal in one step via this edge. And in this talk, I would like to discuss a closely related but simplified question. Okay, now let us look at the graph of this polyhedron P, whose edges are oriented by a given objective function like this. Okay, vertices of this graph are vertices of this polyhedron, and edges of this graph is edges of this polyhedron. And assume no degeneracy for simplicity. And that is, no two vertices have the same objective value. And this assumption, the unique thing of this graph, in this case here, corresponds to the optimal vertex. And a monotone path is a directed path starting from some initial vertex to this optimal vertex. Here, the initial vertex is not specified. For example, this one, and this one are all monotone paths. Then we see that the length of a monotone path, where the length is defined as the number of edges contained in a path, can be regarded as the number of edges traversed by the simplex method for some pivot rule. which is a lower bound on the complexity of the simplex method. So, in the first place, it would be natural to ask how long can the monotone passes be? And in this context, 3 indicators have been discussed so far. For a given polyhedron, its height is defined as the maximum length of the longest monotone path, where the maximum is taken over all objective functions and all initial vertices. So, so the height simulates the case in which we always choose the worst pivot rule for each objective function and for each initial vertex. And the monotone diameter is defined as the maximum length of the shortest monotone path. Okay, so the monotone diameter simulates the case in which we always choose the best pivot rule for each objective function and for each initial vertex. So if we define the pi pivot height as the maximum length of a monotone path following some specified pivot rule pi, then we see that these 3 indicators satisfy this relationship, the sandwich. And another important indicator, a simplified indicator, is a diameter, which is the focus of this talk. Now let us consider the undirected graph of P, where edges are not oriented. Okay. And the diameter of P is then defined as the maximum length of the shortest path between two vertices in this graph, where the maximum is taken over all pair of vertices. And for example, the diameter of this polyhedron P is 3. For example, for this pair, the shortest path length is 3, and this is the maximum. And in general, the diameter is a lower bound on the monotone diameter, as can be seen from this example. Okay. For example, for this diameter path, let us consider such orientation. And then we see that any monotone path starting from this vertex cannot be shorter than this one, because this is the shortest one among all paths, including non-monotone paths. So we have these relationships. Okay. Now I would like to briefly announce some recent results about the 4 indicators. First of all, it is known that there can be a significant gap between the diameter and the monotone diameter. A good example would be the back of polytope, whose monotone diameter is exponentially long, while its diameter is only 2, as shown in this paper. And on the other hand, of course, this gap can be relatively small. For example, for lattice polytope, as shown in this paper. The authors of this paper show that there is a pivot rule, which is a sophisticated one that makes use of the well-known Hausdorff approach, and whose pivot height is given like this. And as I will explain later, the diameter in this case is at most k times d. So
Noriyoshi?
Hi?
I don't know. I don't think the Del Pia Mikini is monotone path. Do they do monotone path? I don't think so.
Not the monotone path. It's a pi pivot height. They give a pivot rule which defines a simplex path. So not the monotone diameter. It's a pi pivot height. I mean, am I clear?
So again, but what is again a pi pivot? How is it defined again? Sorry.
Okay. I want to back. Okay, this is the definition. So pi pivot height is the maximum length of a monotone path following some specified pivot rule pi.
So, but pi is just given at the beginning. It doesn't change,
Yes,
right?
yes.
So then, I mean, I guess what Jesus is saying is in Del Pio and Michini paper, the pi changing at each step or not?
I think it does not change, but I should check later.
Okay, thank you.
Okay, sorry. Okay, and on the height here, as shown in this paper, as well as but examples such as the Cream-Inti cube, the height can be exponentially long for well-structured polytopes, such as the matching polytope. However, interestingly, the authors show that the steepest edge rule, a favorite rule in practice, have polynomial size pivot height for these examples. And here I would like to look at this diameter. Okay. Okay, now let us get into the main part, how to analyze the diameter. Here I show 4 fundamental problem settings. Each problem setting specifies parameters characterizing given polyhedra. Parameters are very important in the sense that they determine tools and approaches that can be used in each problem setting. And the most grasping setting here is to look at d-dimensional polyhedra with n facets, that is d and n as the parameters. Another well-studied setting is to look at linear systems where we can use information from constraint matrix A. There are many parameters. And the third one is to look at the lattice polytopes contained in this d-dimensional cube, which naturally arises from integer programming. And today I'd like to show some recent results in these 2 problem settings. The first setting might be very difficult since we have no major progress for long years, but I want to mention it as it is most fundamental and important. Oh, sorry. So any questions so far? Okay.
No, sorry, just some participant with that was not unmuted, but now we muted.
Oh, yeah.
So that's good.
Thank you. Okay, now let's get into the technical part. I start with the analysis for general polyhedra. That is the first problem setting. Let large delta dn denotes the maximum possible diameter of a d polyhedron with n facets, as defined like this. In this setting, the problem is to determine the behavior of large delta dn. For example, this polyhedron has diameter 3, and hence it implies that the delta 36 is at least 3. And in fact, this is the maximum, and hence delta 36 is 3. Sorry. And in this context, a major open question is whether there is a polynomial upper bound, which is known as the polynomial Hirsch conjecture. And I'd like to know that if the answer to this conjecture is no, I mean delta dn is super polynomial, then the simplest method can never be a polynomial time algorithm, no matter what pivot rule is used. Okay. Here is a quick review on the previous result about the behavior of delta dn. The well-known Hirsch conjecture claims that this value is bounded by a linear function n minus d. But today, the Hirsch conjecture is known to be false in general, even for bounded polyhedra, that is for polytopes, as shown by Santos in 2012. And on the other hand, Rahman showed an upper bound which is linear in n, but exponential in dimension. Okay, and the first sub-exponential upper bound, often called the quasi-polynomial bound, is shown by Kalai and Kreitman in 1992. And these results were improved and extended in the subsequent studies. For example, Rahman's bound is improved by Burnett and also extended for general polyhedra in this paper. And also Santos' counterexample was refined in this paper, providing a new counterexample in a lower dimension. And in what force I would like to look at this sub-exponential upper bound. And here I would like to note that there is a significant gap between the previously known upper and lower bounds on delta dn. Okay, and I would like to introduce a useful theorem provided in the work by Kalai and Kreitman. And here is a statement. If this condition is satisfied, then one has this relationship. Roughly speaking, it says that when n is sufficiently large, delta dn is bounded from above by a linear combination of those for smaller d and smaller n. And the proof is very combinatorial and uses a little complexity and a little geometry in a good sense or a bad sense. And indeed, the same inequality, strictly speaking, a little bit refined one, as well as the upper bound, was shown to continue to hold for more general setting known as base abstraction, as shown in this paper. And I would like to mention the proof here later if there is a time. And this inequality enables us to prove upper bounds on delta dn by induction on d and on n. And I will show you. Okay. Now I will explain a proof method. And I remark that this is motivated by analysis by Todd in 2014, who first improved the Kalai-Kreitman bound. And as I mentioned before, the proof is by induction. And so let P of D be a proposition asserting that some prescribed function f is indeed an upper bound on delta dn in some dimension d. Okay, this is a proposition. So we want to prove this proposition is true for any d. And the base step is to prove P of D in some dimension, say L. And this can be done by using good upper bounds in low dimensions or by computer, or the linear upper bound in fixed dimension shown in this paper. We can prove, anyway, we can prove this base step. Okay, but the inductive step is to show P of D by assuming that P of D minus 1 is true when D is greater than or equal to L. And this is done by induction on N. So here is an image of this proof. Okay. Now suppose D is fixed and P of D minus 1 is true. Let us consider the case when N is less than 2 times D, which will be the base step of this proof by induction on N here. And it is known that the value of delta, large delta Dn, is always attained by simple polyhedra. So together with this assumption that n is less than 2 times d, this fact implies that this inequality holds. This is because in a simple polyhedron, every vertex meets exactly d facets. And from this assumption, there must be a common facet. So this is a facet. Its dimension is d minus 1, and the number of facets is at the most n minus 1. So we have this inequality. And so in this case, using this inequality, we have this inequality. And from the induction hypothesis on D, we have this inequality. So if F satisfies this inequality, then we are done. So let us call this inequality condition 1. Okay. So if this is satisfied, this is at the most this one, and this is at the most this one, and this is at the most this one. So we are done. Okay. And now let us consider the case when n is greater than or equal to 2 times d here. And in this case, we can apply the inequality of the Karaite-Reitman since the condition of the theorem is satisfied. And on the other hand, we can assume that the desired inequalities between delta and F is satisfied for the case with d minus 1 n minus 1 and dn over 2, like this, from induction hypothesis on D and induction hypothesis on N. Okay, so again, we make such assumption. So if F satisfies this inequality, then we are done, because this value is at most this one, and this value is at most this one, and this value is at most this one. So if we have this inequality, then we are done. Okay. So to conclude, this proof method ensures that if F is a function such that these two conditions are satisfied for all n and d greater than some specified L, and if we can show that F is indeed an upper bound on delta in dimension L, then we can conclude that F is an upper bound on delta for D larger than or equal to D, to L. So informally, we want to solve such an optimization problem to find a good upper bound on delta dn. So this is the proof method. So then it will be natural to ask what is the best possible upper bound derived from this method. As I mentioned before, the proof method is motivated by the analysis by Todd in 2015. He proved such an upper bound. So this is the first improvement of Karaite-Reitman bound. And he mentioned that this bound fits better to Hirsch's bound, n minus d. Indeed, it coincides with n minus d if d is 2. Okay. And also, he also mentioned that it is nice because it coincides with data when n is equal to d. In this case, when n is equal to d, data is 0, and this bound is also 0. Okay. So, and here is a upper bound by myself, which is derived from the proof method I mentioned. So here is a background of this result. In view of Todd's result, I thought that it can be interesting if the exponent here is reduced further while keeping this function form. Okay, so this was my question. Can we do better in the form? Okay, And we see that it is possible by starting the proof by induction on dimension D in high dimension, which might be a common technique. So the answer to this question, yes, but this time G of D was still in order D, such as D over 4 or D over 8 or something like that. So then my next question was, can we beat the barrier order D? And then the answer turned to be true. So, but the analysis is just technical using such formulas. Okay, and here's a comment by Jules Calais in the Handbook of Discrete and Computational Geometry. He mentions Toto's bound here. Recently, a small improvement was made by Toto, who proved that here. Okay, this is a statement. And he also points out such an open problem. Okay? Even upper bounds of the form like this for some c less than 1 would be a major progress. And this function can be written down as n minus d to the power of log of order d to the power of c for some c less than 1. Okay, and you can check that this is better than my bound. Okay, so my result is not a major one in this definition. So here's a question: can we achieve? I have these two questions. Okay, and I'm sorry, but I have no idea about the first question, but I want to announce it as it is a fundamental question. And the answer to the second question is would be no with high probability, but I'm not sure how to conclude that one can never derive such an upper bound from the inequality. How? So yeah. And but on the other hand, I also want to remark that my analysis in this paper can be refined, I think, since it uses approximations such as like this one. Okay, that's all for the first part of part 2. Any questions so far?
Yes,
Okay.
Daniel.
Yeah, I was just curious. So it's not possible to say that, you know, any function that satisfies the required recurrence relation starting, you know, for, I don't know, dimension 2 or 3 being tight, is at least quasi-polynomial?
Sorry, could you repeat again? Sorry.
So you have these like requirements on the function, the C1 and C2. And so it's not possible to show that anything that satisfies C1 and C2 and is, you know, I don't know, reasonable for dimension D equals 2, like has to be at least quasi-polynomial? Or like has to have at least exponent 1 in front of the logarithm?
Oh, could you discuss later?
Sure.
Sorry.
Sorry.
Sorry. Thank you very much. And sorry. Yes. Okay. Okay. Now let us get in the next part. Analysis for lattice polytopes. So in this problem setting, we define small delta dk to be the maximum possible diameter of lattice polytope contained in this cube. So d and k are the parameters. The problem is to determine the behavior of this small delta dk And important special cases are Z1 polytopes and half-integral polytopes, which play an important role in discrete optimization. More generally, any rational polytope can be regarded as a lattice polytope by clearing fractions. I mean, by multiplying the least common multiple of the denominators. Okay, let me start with a quiz in dimension 2. What is the behavior of delta 2k? That is a maximum possible diameter of lattice polygon contained in the square area of length k. Okay. And here, please note that we now want to maximize the number of vertices, since the diameter is just half of the number of vertices in dimension 2, roughly speaking, about almost half. And it is not difficult to see if when k is 2, when k is 1, the value of delta 2, 1 is 2. Since we can take all these 4 integer points as vertices, so in this case, the diameter is 2. And what if k is 2, delta 2, 2? Of course, we cannot take all these 9 integer points by convexity. But we see that in this case, the value is 3, which is attained by such a hexagon. And thinking in the same way, we may see that small delta 2, 3 and small delta 2, 4 are both 4, like this. Okay, and here's the question. Is delta 2k linear in k or sublinear in k? Okay, and please guess if you're interested in. And here is the answer. The answer is that delta 2k is sublinear in k. More formally, when k goes to infinity, one has this estimation, where this symbol means that the ratio of the two functions converges to 1 when k goes to infinity. So here, please note that the exponent is 2/3. Okay, so this means that 2 consecutive values take the same value. I mean, fails to increase with high probability when k is sufficiently large, which might fit our intuition. And the proof is a direct consequence of previous results, where the number of edges or the number of vertices is discussed instead the diameter. And recently, we obtained a result that can be seen as a generalization of this result into high dimensions. Here, I'd like to introduce this result. Okay. First of all, before getting into the technical part, I would like to give a quick review. In this context, the most classical result is the one by Nadev for the case when k is 1. Namely, he showed that the diameter of Z1 polytopes in dimension d is at most d, and shows that it is tight. And this upper bound is later generalized for any k by Klein-Schmidt and on. And recently, Del Pia and Mincini defined this bound for k greater than or equal to 2, and showed that it is tight if k is 2. And further refinement is achieved in this paper. Okay. And on the other hand, when k is relatively small, when k is less than 2 times d, delta dk is known to be at least about half of this Klein-Schmidt and On's bound. k plus 1 times d over 2. And also, as I mentioned before, asymptotic tight bound is known in dimension 2, only in dimension 2. And previous results can be summarized by using such table. The horizontal axis corresponds to the value of k, and the vertical axis corresponds to the value of d. And for example, another result for the one polytopes reveals the values here, and those by Delphi and Minci reveals here, and the asymptotic bound in dimension 2 reveals here. Okay, and I here remark that the value of this cell this cell is still open, although one could expect that it might be 2 times d from these low-dimensional results. And in view of this table, it would be natural to ask whether we can generalize this asymptotic estimate into higher dimensions. And it was mentioned in the paper by Delphi and Mincini that for any fixed d, we can show a asymptotic lower bound like this by considering the Cartesian product of polytopes using this result. Okay, and they also mentioned that it might be an interesting open question whether this lower bound can be improved or not. And our result answers this question, and the answer is yes. Okay. And here is a highlight of this paper. The basic strategy is to look at the special case of lattice polytope, which is called a primitive zonotope. This primitive zonotope has already been utilized in this paper to provide good lower bound on delta dk, as I mentioned earlier. And an important thing is that this relationship. Okay, primitive zonotope is a special case of lattice zonotope, and lattice zonotope is a special case of lattice polytope. And what we proved here is the asymptotic diameter of primitive zonotope. But this asymptotic estimate has nice properties. First of all, this asymptotic estimate coincides with that of lattice zonotope, okay, for any fixed d. And next, this asymptotic estimate coincides with that of general lattice polytope as well as lattice zonotope in dimension 2. Okay, and finally, it provides an improved lower bound on that of lattice polytope in n dimension compared to the previous lower bound. Okay. From now on, I would like to explain the proof sketch. I start with the definition of the primitive zonotope. We call an integer vector g, which is not the zero vector, primitive if its GCD is 1. Here, GCD is the greatest common divisor of the elements of the vector g. And now let PD denote the set of primitive points in dimension d. And the primitive zonotope is a Minkowski sum of line segments called the generators, given like this, where G sub I is a primitive point. So here's an example. Let this point be an origin, and these 2 points are then primitive, 1, 1, and 2, 1. Okay, and so using these, we can construct a primitive zonotope like this. So these are the generators. And if we add one more line segment like this by focusing on this primitive point, we obtain this primitive zonotope. And thinking in the same way, we see that all of these the primitive zonotopes. Okay, so this is a definition. Okay, and a lattice zonotope is defined by replacing P of D by ZD, that is a general lattice point of general lattice points. So primitive zonotope is a special case of lattice zonotope. Okay. Now I'd like to state the main theory of this paper. For any fixed D greater than or equal to 2, if we let delta Z dk denote the largest possible diameter of lattice zonotope contained in this cube, D-dimensional cube of length k, then when k goes to infinity, one has this estimation, where C of D is a function that depends only on D, and hence is a constant in fixed dimension. And here, zeta, this symbol denotes the Riemann's zeta function, and one can verify that the C of D converges to 2 times E, which is approximately 5.47 when D goes to infinity. And please recall that what we wanted to know was the behavior of delta dk, but what we revealed here is the behavior of that of lattice zonotope, and by focusing on its special case, primitive zonotopes. And now let me explain how good the estimate is, how good our result is. And to this end, let us look at the case in dimension 2. And since the value of zeta function when these two is given like this, as known as the Basel problem, the estimate in the theory will be like this. Okay. Hence, in dimension 2, the symptotic diameter of lattice zonotopes coincides with that of lattice polytope, as I mentioned earlier. This is the same as the constant I mentioned earlier. So to conclude what I mentioned so far, when k goes to infinity in dimension 2, these three have the same asymptotic bound: primitive zonotope, lattice polytope in dimension 2. And for any fixed D in higher dimension, these two have the same asymptotic bound. But we are not sure about here, which is remained as an open question. Okay. And as I explained earlier, it was pointed out by the authors of this paper that when k goes to infinity, delta dk is bounded from below by this quantity. Since delta zeta dk is a lower bound on delta dk for any dk, the asymptotic estimate of delta zeta dk in the main theorem implies that when k goes to infinity, one has this estimation. Okay. And please note that the hidden factor here, C of D, converges to a constant at most 6, as I mentioned. And while the hidden constant here is D. So, however, for any fixed D, this estimate is better when k goes to infinity, since the exponent is strictly greater than this one. Okay. Okay. Finally, I would like to show you some technical parts more in detail. It can be easily shown that for zonotopes, including primitive zonotopes, the number of generators equals its diameter, as long as generators are pairwise non-collinear, as you can see from these figures. And our proposal is to look at a set of primitive points defined like this. Here, P is a positive integer, a parameter controlling the size of this set. That is the number of primitive points contained in this set. And we see that the resulting generators will be pairwise non-collinear from the fact that each endpoint is primitive and this condition. And this condition means that the first non-zero element of G is positive. And roughly speaking, the diameter of the resulting primitive zonotope will be large, and its size, that is the value of K that contains the resulting primitive zonotope, it will be small because we gather all the short line segments in this sense. Now I'd like to show you some examples of the set script G in dimension 2. Let P be 1, and in this case, this set consists of two primitive points, 0, 1 and 1, 0. And for example, 0 minus 1 cannot be included as its first non-zero component is negative, and also 1, 1 cannot be included as it violates the norm constraint. And thinking in the same way, we see that if P is 2, then the set is given like this. And note that, for example, 02 cannot be included as it is not primitive. GCD of this vector is 2. And if P is 3, then this set consists of 8 primitive points. And this is an image of the resulting primitive zonotope in this case. There are 1, 2, 3, 4, 5, 6, 7, 8 primitive points here. And now I introduce these three notations. HDP denotes the primitive zonotope defined by this set script GDP. And delta dp denotes the diameter of this primitive zonotope, that is the number of primitive points contained in this set. And kappa dp denotes the minimum k, that is the size that HDP contained in this d-dimensional cube. And for example,
yeah, I just wanted to ask a question. So you mentioned a fact on the previous slide that the diameter is exactly the number of number of generators. Is that, I guess, is that easy to see? I think I can see it in 2D, but like in higher D, is there an easy argument?
Yeah, for example, one can use a theorem about Cartesian product. Yeah, we can show how to show this. Yeah, this is true in general in any dimension. But,
or just like, I mean, I guess you want to create a path that uses like one generator at a time, and you just need to make sure that each of those generators are edges. Yeah, I mean, right. The question is, how do you make sure that they're always edges? You know, that you don't like accidentally go inside.
Inside. I can show you the proof later, but I cannot. I mean, I cannot explain now concisely, but I know the proof. Sorry. Okay,
Yes.
sorry. Okay, so yeah. Okay, so and here is the outline of the analysis. First, we propose a symptotic behavior of the delta dp when p goes to infinity, and as I will explain in the next slide, one can apply a previously known elegant formula here. And next, we provide a symptotic behavior of kappa dp, which is a more technical part. And then in the step 3, we relate the kappa and delta by making use of an underlying structure of the set script G. And finally, by eliminating P from these estimates, we obtain the desired result. And okay, and so I just explain how the step 1 can be proved. And please recall that we call an integer vector G primitive if its GCD is 1, and PD denotes the set of primitive points in dimension D. And the density of PD primitive points over the lattice points is known to be the inverse of zeta D. And for example, in dimension 2, the density is about 60%. Here, the points in purple represent primitive points. And furthermore, it is known that for any convex body C, the density of primitive points over lattice points restricted to the region defined by the dilation of C by P, like this, converges to the inverse of zeta D again. So we can use this result. Okay, so therefore, to obtain the asymptotic estimate of delta dp, that is the number of primitive points contained in the set script G, it suffices to set PC to the L1 number of radius P in the formula here, and have the result. And this is an image. The set of primitive points satisfying the L1 norm constraints here, lattice points appear in this region. Okay, and exactly half of them satisfy the condition that the first non-zero element is positive, as can be seen from this figure. And so, like this, we can estimate the symptotic behavior of delta dp. And that's all for the second part of my talk. Any questions so far? Although I'm really not good at answering the question, sorry. Okay.
No, okay. No.
Okay. Can I get it to the part 3? Okay. Any questions?
Yes.
Thank you. Okay. I'd like to finally, I'd like to introduce some open problems on part 2. So this is the main theorem of our paper, and we show that delta z, the value for lattice zonotape, is the symptotic estimate of delta z dk is the same as that of delta dk, general lattice polytope in dimension 2, but we are not sure this holds in higher dimensions. So this is an open question. And a promising approach would be to try to approximate delta dk by delta z dk, more formally considered to translate any lattice polytope P whose diameter attains delta dk into a lattice zonotape contained in delta dk prime with k prime close to k, but so far we have no good result. And another open problem is here. As mentioned earlier, we are still not sure about the behavior of delta D3 when k is 3. Although one can expect that it is 2 times d from this column. And in my opinion, even a proof that is specialized for this case is interesting. And also, here's a question by Antoine. Can we show that delta zdk is equal to delta dk for nd and k? And indeed, all pair of dk, we know the exact values of delta dk. This inequality holds. Okay, that's all for my talk. Thank you.